it begins to glow. Okay, so it glows. What is glowing? Oh my gosh. Glowing is emitting its own light. Basically, it's emitting light because you made it hot. So basically, you made it hot and it begins to glow. Okay? But there is a certain aspect about the color it glows. And actually, this applies to stars. Have you ever heard it's glowing white hot? Okay. The color that something glows is an indication of the temperature. And so actually, we can see that phenomenon in this wrought iron. Okay. So it gets brighter, okay, and it changes from red to white. Okay. It gets brighter. It's called Law 1 of radiation here in a minute. It gets brighter. The fact that it changes colors is Law 2. Okay. So as an object becomes hotter, it increases its temperature. We've talked in here, I know we talked about the fact that all matter is in motion, and the temperature of matter is an indication of its motion. Didn't we talk? Yeah, we talked about kinetic energy. Okay, and so basically hot, okay, it's going fast, okay, it becomes brighter. That actually is called, it's part of Stefan Boltzmann's law. Okay, Law 2 we saw was the change in color. The dominant color, all that means is the color it appears as. Dominant color is the color it appears as. I'm going to kind of show you these color curves or these radiation curves. And honestly, even though it looks orange, it's got all the other colors. It's just orange is the highest one, the most intense one, the dominant one. Okay? So the fact that the color changed from orange to white is actually Wien's law, Law 2. Okay. What's what? The temperature? Is it like hidden from you? Yeah. Okay. The thing's in the way? What's the third word? Reddish. Reddish? Yeah. Reddish. Thank you. So to kind of combine Stefan Boltzmann's and Wien's law, okay, if we look at a cool object, okay, if it's cool, it's going to appear to be reddish and its intensity is going to be kind of low. Okay, if it's cool. If it's hot, its intensity is going to be jacked up and the color is going to be a shorter wavelength. Okay, more bluish. Because remember, like Roy G. Biv, B-I-V, blue, indigo, violet, those are the short wavelengths. Okay, and they go for hot objects. So right away, we already finally get to some star stuff tonight. So have you ever looked up at the sky and seen a kind of an orangish star, kind of an orangish or reddish star? It might have been Mars, but it also might have been, some stars are red, okay? And they're cool, okay? Those intense blue stars, they're hot. Bada boom, okay? Go out and amaze your friends, okay? So, like I said, even if something appears red, it actually still has the other colors of the rainbow. It's just red is the most dominant. Okay? So what we do is make these radiation curves, sometimes called black body radiation curves. But here's your look at radiation curves. Okay? I'm going to see if I can move this. So each little, we'll kind of take a look at the X and Y axes. Along the x-axis is wavelength, and along the y-axis is intensity. Yeah, this is working, guys. That shadow's funny. That's better, isn't it? Okay. Oops. Okay. So, along the x-axis is wavelength. Okay, so down here we have wavelength. Okay, notice that we have, right here, we have Roy G. Biv. Okay, oops, there it goes. So actually we have long wavelength here and short wavelength here. Does that make sense? what's chopped off over there is 10 to the 5th behind the telescope. And that is how long the wavelengths are in meters. So they're radiation curves. Basically, oh yeah, and along the y-axis is intensity. This is just intensity. So basically, they're saying that this particular one is most intense, okay, at that wavelength. Okay, this one is most intense at this wavelength. Okay, you get the idea. So here we go. Here are those 4 radiation curves, different objects. The blue one, now notice it's higher, so its overall intensity is higher. Okay, that's Stefan-Boltzmann's law. Okay, and it's shifted over here to the shorter wavelength. That's Wien's law. Okay, it's the hottest of those 4 objects. We talked about temperature scales. K, of course, is Kelvin temperature scale. And by the way, these are surface temperatures. If you want to look at the core of that star, it's way, 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 way hotter. All right, so the next one, okay, oh, that's our sun. The yellow one, so the surface temperature of the sun is about 6,000 Kelvin, about 5,800 Kelvin, okay? Notice that its intensity is lower than the 15,000 Kelvin star, and it's shifted over to the longer wavelength. Okay, then we have a star that's about 3,000 Kelvin surface temperature, a cool 3,000. Okay, notice that it is shifted over even more for the longer wavelength, and it's squattier. Okay, Stefan-Boltzmann's, Wien's law and Stefan-Boltzmann's law. The last one, is that not adorable? It's a human. I just think that is cool. In general, if we were to take a look at the radiation that anybody's oozing, we kind of have a peak here in infrared. What's that? Oozing. It's true. Oozing out that energy. Okay? But we're not glowing, but we're oozing energy, right? So, like for instance, if you're like in the military, one of the things that they use are those infrared goggles. Okay, so they look for thermal signatures. I think hunters do that too, don't they? Kill Bambi. No, I'm just kidding. Okay, so that's very helpful. I love that idea. Right away, you can go out in the nighttime sky, look at different colors of stars, and tell something about them. Now this Doppler effect or Doppler shift, you can't really naked eye see it. Okay, I'm going to kind of describe it to you. It works with light, and it also works with sound very well. So this says picture an object that is glowing, emitting EM, remember that's electromagnetic radiation, that's any of these, it's glowing energy, okay? And picture that object coming towards you, okay? You're an observer and you're stationary, you're sitting still. So that object's coming towards you, emitting radiation. The Doppler effect says basically the radiation that it's emitting in your direction, since it's coming your direction, actually those energies, the wavelengths will be squished together. So they won't be so long. So actually they'll be shifted towards the blue end. It's called a blue shift. Okay? It is so cool. We see this in stars. Stars that are moving towards us are blue shifted. Okay? So stars that are moving towards us, or any object that's moving towards us emitting radiation, that radiation is blue shifted. So now let's switch it up a little bit, and let's say that the object that's emitting the light is moving away from you. And I can almost see this, okay, as it's moving away from you. You could see the waves, the energy that object is emitting lengthen. Okay, so if it lengthens, we're going more towards the red end of colors anyway. It doesn't have to be visible light. But whatever energy it is, the wavelength will get longer. Okay? So we call that a redshift. And that is actually one way that we can tell how fast something's coming towards us or going away from us. By this, it's called the Doppler effect or Doppler shift. Carbonaro effect. Anybody watch Carbonaro effect? Okay.
Is it Carbonaro effect?
Yeah. Good show. It's this magician.
Yeah, I like him, but I don't have time to watch him all the time.
Yeah, we haven't seen him for a while either. I don't know. But
Well,
it's funny.
I watch the old ones because I'm behind, but
Yeah. When you should take a break one of these days and watch Carbonero.
oh, he's
In
funny
fact,
too.
he is funny. I don't know how he does that. So I said this blue shift, red shift, one fish, two fish, red fish, blue fish. Blue shift, red shift actually can also work with sound. So here we have a train, okay? Notice that train is stationary, but that train is emitting a sound, okay? And that train is going to go, I think, from left to right. So actually, with regard to the sound waves, can you see where the person on the right who is getting the train coming towards them, the pitch actually goes up. It's kind of like the wavelengths get shorter, just like the color of light gets shorter, so the pitch will go up because the sound wavelengths get shorter. So, like for instance, if you've ever been outside and heard a car coming, it goes okay, same thing. Okay, when it's coming towards you, you hear the pitch ramp up. That's the blue shift. When it's going away from you, you hear the pitch get lower. That's a red shift. Okay, and so that's with sound, and this is with light. Now, so here we have a light bulb is moving in that last diagram. Light bulb is moving just like the train was moving to the right. And so that person on the right sees a blue shift, the person on the left sees a red shift. So let's take a look at how that works. You recognize you don't have to tell me what element it is, okay, but the bright lines are emission spectrum. Okay, so that's our lab sample. And then we get a picture of stars with those same set of, we call those spectral lines. Okay, and if you compare the top one with the second one, can you see where the second one is the same lines, but they're shifted over to the right? And that to the right is a red color, so actually that's a red shift. So we actually know that that star emitting that second set of lines compared to the lab sample is moving away from us. This star is also moving away from us, but can you see where it's shifted even more? Okay, so the first one's the lab sample, the next two are stars that are moving away from us. They're exhibiting a red shift. The second one's moving even faster because bada boom. Okay, so here now, you have to compare the top one with the fourth one, the top one with the fourth one. So now can you see where it's the same set of spectral lines, but they're moving over here to the shorter wavelength? Okay, so that's a blue shift. Okay, so that blue shifts happen when the star is moving towards you. So the last one actually is also a blue shift, but it's even more of a blue shift. Okay, so to understand this star down here is object 4, you have to compare it with the library sample. So library sample versus number 4, shifted over here even farther to the left, okay, the shorter wavelength. It's going faster towards us. But there's a catch, okay? This only works with what we call radial motion. It only works with kind of like direct line of sight. If the motion is in direct line of sight between the observer and the object that's emitting the information. So we call that radial motion. The opposite of radial motion is proper motion, and it's like at a 90-degree angle. So in these two scenarios, object 1 is going away radially, radial motion. Object 2 has proper motion. Okay? So object 2, we're not going to see any red shift or blue shift. No Doppler effect for object 2. Object 3, though, kind of states what usually happens. Actually, objects moving have both a radial component and a proper component. So we can only get a fix on the radial velocity, not the proper velocity. Honestly, for object number 2, I'll tell you how we usually see it moving, if we can. We usually see this moving against the background stars. Okay? That proper motion. Telescopes. Dun, dun, dun. Okay, so I brought an example of a telescope here tonight, okay? But whatever telescope it is, basically, it has a tube, okay, a shaft, and whether the collecting device is here with a lens or here with a mirror, basically it's taking a bunch of energy from a star and gathering it to what we call a focal point. And that energy, those energy pieces are called photons. So sometimes we call it a photon bucket. So telescopes are gathering photons, concentrating them so we can kind of see them in a cute little packet. So since it's concentrating those photons in one little area, okay, it allows us to see things that are really dim. It gathers that light so we can see them brighter. Okay, we can see things with more detail than we can with the naked eye. It allows us to kind of make sense of dim objects. We can see the detail. Okay, and the other thing is we're lucky then we can actually, compared to our naked eye, see things at farther distances because it's gathering that remote little tiny pieces of light into a little bundle, okay, and unpacking it for us to see it. So there's two types of telescopes. There are the type of telescopes that use mirrors. And now, I like mnemonic devices and the beginning letters of words and that sort of thing. These two types of telescopes both begin with the letter R. So honestly, I mess them up sometimes. But you can't mess them up. I'll be out at the observatory or whatever trying to tell somebody what kind of telescope it is, and I will mess them up. But reflecting telescopes use mirrors. Reflecting telescopes use mirrors. Sometimes we don't call them reflecting telescopes, we call them reflectors. Okay, reflecting telescope, reflectors, the same thing. The other type of telescope, and I didn't bring one of those here tonight, but I will one of these days, and uses a lens. The other type of telescope is kind of, we tell kids, it's like your eyeglasses. Okay, it uses lenses. So you can hold your eyeglasses out there. Basically, it's bringing light to a point. Okay. So kind of from left to right, actually, this is a reflecting mirror. Okay. There's a mirror back there, and this is a refracting mirror. So on the long one, refractors tend to be long. Refracting telescopes that use lenses, okay, they actually have the light gathering place at the end of the tube. I hadn't thought about it till just now. The ones that use mirrors have the mirror at the butt. So actually the mirror here is right here at the butt. So this is a refracting telescope. Can you see the little mirror down there? Yeah. It looks like that button thing is in the way, doesn't it? Yeah, I'm going to talk about that. Okay. It is kind of in the way. So we would call this a reflecting telescope. Like I said, sometimes I get them mixed up. And a refracting telescope uses lenses. Okay, so a little bit about they make objects brighter. They also allow us to see details on objects. For instance, if Mars is in good viewing, okay, you actually can make out a little bit of the polar caps of Mars. Okay. Yes.
Okay, so I know this is kind of random, but I was wondering why we didn't have a lab last week. I think it was
2 weeks ago.
Well, the moon was orange every single night.
Yeah. I jumped the gun 2 weeks ago. Was it 2 weeks ago? We were supposed to have a moon lab, I think.
I don't know.
And it was, we could have seen the moon, but there was no reason other than I thought it was going to be cloudy. But the reason the moon's kind of been orangish is I've read that it's because of forest fires out west. Yep.
That makes sense.
Yep. The extra stuff in the Earth's atmosphere kind of give that hue to it. Yeah. So the thing about detail, sometimes what's helpful is something called angular resolution. So remember we talked about the altitude of an object is the angle, right, above the horizon. That's altitude, and you can kind of use your hands to kind of get a sense for degrees. Well, that's the same thing we're talking about when we're looking through a telescope and saying, oh, I can see Another cool thing is detail to see is actually the bands around Jupiter. Okay, Jupiter actually has bands that alternate. Jupiter's bands go this way, and then they go this way, then they go this way, then they go this way, belts and zones. Okay, so to actually see those bands, okay, that would be an angular resolution issue. Can you see them, or are they all blobby? Okay, so good angular resolution gives you minute detail. Okay, so this actually is 8 inches. I know, we just have to kind of ignore the little thing in the middle, okay? It's got to be there for the type of telescope it is. But back here, the diameter of this mirror back here is 8 inches, okay? So in general, if you went 16 inch, so actually at the observatory, one of the telescopes is a 16-inch reflecting telescope. If you go 16 inch, if you double the diameter, you quadruple kind of the resolving power or the angular resolution. Yeah. This is double. Maybe do double. That's quadruple. I'm going to go with double. I'm going to put on the test. Okay. So there's 2 types of telescopes. This one uses mirrors. The other type of telescope I want to talk about is the refracting telescope that uses lenses. So just a little bit about what refraction is, okay? Refraction is basically light going from, or light can be refracted as it goes between 2, what we call medium. So actually right here, if you take a piece of glass and put light at an angle, okay, that light is going to be bent, just like it's being shown here. Okay, it's going to be refracted as it goes from air to glass, and it's going to be bent again as it goes from glass to air. It's going to be bent twice. We call that refraction. Refracting telescope, okay, that's what it does. Okay, so as it goes from air to glass, okay, it is refracted. And as it goes from glass back to air again, it is refracted again. It's bent. Now that would not make a very good telescope lens. Okay? What makes a good telescope lens is a double convex lens. I had to remember my old physics days. Okay? So over here, this is actually what's at the end of your optical tube if it's a refracting telescope. So have you ever killed ants with a magnifying glass? I know. You ever tried to start a fire with a magnifying glass? Okay, that's better. Okay, so basically what you did was to take the sun's rays and you basically kind of move your magnifying glass up and down to find the sweet point, basically to have the focal point of that magnifying glass just concentrate all that light on that thing you want to burn. Okay, that's it. And so it's the same thing with refracting telescopes. They take all that light that traveled, hundreds of millions of years to get here, okay, to a single point, and then I say it's what we call unpacked, and we kind of set it through an eyepiece. When it's unpacked, the image can be kind of inverted and that sort of thing. Okay, but the focal point is the cool point. That's a big refractor. That actually is near in the Chicago area, Yerkes Observatory. At the Whitty Observatory, we have a refracting telescope that's got a 15-foot, nothing like this, but 15 feet, that's pretty long, optical tube. At the end of it, it has a lens that has a diameter of 12 inches, which is pretty big. This, what's that?
Oh, it doesn't even look that big. And I saw the person next to me.
Yes, exactly. Yes, Nellie's pointing out, when you see the little person here, you're like, oh, okay. That kind of, yeah. And I have friends that have been to this one, and actually the whole floor raises up and lowers. Because, depending upon where you need to put the telescope. Oh, my God. But you see the slit, and that's, of course, where you would turn the optical tube to look outside. So 1 meter would be like a yardstick. Okay, that's how big the lens is on the end. The thing about lenses, have you ever heard that glass is like a slow-moving liquid? Glass over time will become deformed. If you've looked at old houses with their window panes and you can kind of see deformations, glass will eventually kind of settle. Gravity makes glass do that. So actually there's a limit to, when you make a lens for a telescope, there's a limit to, and that's pushing the limit right there. Largest refractor in the world. Because you figure if it kind of becomes deformed, then that screws up your image, right? So, pretty cool. Okay, so we're switching gears. Do you see how we're switching gears from refractors to reflectors? This is kind of showing you what a reflector telescope would look like. There's actually 4 kind of versions of a reflecting telescope, but what they have in common is they have the mirror at the back of the optical tube. The mirror's at the back of the optical tube, okay? So light comes in, hits the mirror. Now, instead of being convex, actually it's what we call concave. Looks like a cave. Hopefully, though, it's not just directly concave. Hopefully it's parabolic. Okay, it's easier to make a spherical concave than a parabolic concave. I don't know. So I'm told. And so for that reason, you have to kind of use what we call a Schmidt correcting plate. I think that's what that's for. But anyway, so the focal point is actually in advance of the mirror. So it comes down the tube, okay, it hits this sort of mirror, that's this nice shape, and it all goes back to a focal point in front of the mirror. So you're like, all right, how do we get that information? Well, that's what gives you 4 different types of reflecting telescopes. Say you're reflecting 4. So it's not in your slides, but I'm going to go ahead and show you which sort of reflecting telescope this is. Okay, so you guys don't have this one. Kind of in the order of their popularity, this is what we call a Newtonian reflecting telescope, So notice that the light is coming in. Okay, you see your mirror at the bottom there. Okay, so here comes the light. Choop, choop. Okay, it hits the mirror down here and it goes back up to a focal point. Okay, and so the focal point actually is here. Notice by the way, the reason it's bent like that, 2 reasons. Well, not the reason it's bent, but the fact that it's bent, this is where you can put this is my eye. Okay, that's where you can put your eye, right there at the side of the tube. I've got one of those too. It's a Newtonian design of a reflecting telescope. So what that means is it needs what we call a secondary mirror. So this thing right here, okay, that is a secondary mirror. Secondary mirror. There's been a few times in my slides, I think leading up to this point, I talked about a reflecting telescope and its primary mirror. Well, its primary mirror is this one down here. Okay, that's the one doing all the work. So you have your primary mirror doing the light collection, and I'll go ahead and post this out on, I'll send it to you, the slide. So there's 4. That's not this kind. This is this kind. So there's the Newtonian design, very popular, and then there's the Cassegrain design. This is a Cassegrain design. Okay, so notice similar, since it's a reflecting telescope, you have to have your mirror. So this is your primary mirror down there, okay, at the base of the telescope. Okay, so the light comes in, okay, it is brought back to a secondary mirror, okay, so this right here, actually that is that annoying little button that we can see from here. So that is your secondary mirror. And then what happens from a secondary mirror is it is sent back down, okay, so that you look at it right here. You look at it right here. So that's this design. It's a Cassegrain. So goes down there, it hits that 8 inches, it goes back, it's what we say folded, is that not a cool word or what? It comes, there's a secondary mirror here that's actually gotta be flat, right? And then it's sent back to come out to that. There you go, Cassegrain. And it has what we call a Schmidt correcting plate. So actually this is a Schmidt Cassegrain. It says here, it says Cassegrain, but before it has Schmidt. And the Schmidt, I'm pretty sure, is to kind of compensate for it not being parabolic, but being really more spherical. So. The other two look like this. This one makes sense to me, okay? It's actually, it's kind of a catch-all coude focus, where notice it has 2 secondary mirrors, you know, so I'm going to, here's a secondary mirror, kind of like the Cassegrain design, and another secondary mirror, and then this is where you have your eye. Oh my goodness, I have hair on the eye. Okay, so that's where you put your eye. The last one makes me giggle. Okay, it's a prime focus, so it looks like this. Prime focus, basically, notice where is it, there's no secondary mirror. So prime focus, a person goes and sits right there at the focal point to gather their data. I just think that's kind of funny. And I'm thinking I've seen one, a humongous telescope, some sort of reflecting telescope where there's like a little chair there. I don't know. I think that's funny. Okay, so just some pictures of some telescopes. Oftentimes, you can't see it in this one, but in order, for instance, to get an 8-meter diameter mirror, a lot of times they actually kind of segment the mirror pieces and then make that parabolic shape, which comes in handy like when they need to reshape the mirror. And I'll kind of show you like the last slide in this part. So this is the same as this, isn't it? This is that Cassegrain where it comes out the butt. You can kind of see the segmentation on this one. Okay, there's that little guy right there, or a little guy. Kind of see the, what are they, hexagonal little slabs that kind of all work together. Road trip, Hawaii. They got his and her domes, Keck 1 and Keck 2. It's a busy place there, I guess. We're kind of switching topics. So actually, let's take a running start at this on next week. Because the next chapter, I'm thinking there's some really cool videos. The next chapter is on the formation of our solar system. Sounds like a universe series, I don't know. So we'll finish up. There won't be any homework due, which works out fine because I'll bring homework sheets next time. I'll bring homework sheets next time.
Oh, I was going to say, here's the room.
Okay, thanks.
If you want a copy of it.
I got it. Thank you, Susan. You're so
So no homework due?
No homework due. Nope. But don't tell anybody else. Just kidding.
Where do you want them to be?
What's that? Oh, yeah, just start a pile up here. Thanks. And watch yourself going out tripping and all